The research paper presents a novel approach to predict the solid-liquid phase boundary of molten salts using thermodynamic integration and neural network potentials trained on density functional theory data. The method combines the computational cost advantages of classical force fields with the accuracy of DFT, enabling first principles prediction of phase diagrams in molecular dynamics simulations. The authors utilize the Fumi-Tosi potential for classical MD simulations and neural networks as universal function approximators to describe the complex multidimensional potential energy surfaces of atomistic systems. They employ various exchange correlation functionals, including those that explicitly include dispersion interactions, which show better agreement with experimental data over a wider range of temperatures and pressures. The study highlights the sensitivity of the predicted phase boundaries to the choice of exchange correlation functional and demonstrates a method for predicting solid-liquid phase boundaries for any material at an ab-initio level of accuracy. The authors discuss two approaches to predict the solid-liquid phase coexistence of materials. They first describe direct interface coexistence simulations, which have limitations due to the dependence on the orientation of the interface and the slow velocity of the interface close to the melting temperature. Alternatively, they employ thermodynamic integration, which involves constructing a reversible pathway between the two states. This method is used to predict the phase coexistence from the free energy difference between phases as a function of thermodynamic variables. The authors then outline a three-step scheme for predicting the solid-liquid phase boundary of sodium chloride using neural network potentials, NNPs, trained to density functional theory, DFT. They detail the first step, which involves a four-step reversible pathway from liquid to solid at a single state point, and discuss the results of the method, including the estimation of the Gibbs free energy difference between the solid and liquid phases, which can be used to determine the melting point. The study highlights the limitations of classical potentials and emphasizes the importance of considering both the solid and liquid volumes near the melting point for accurate phase boundary predictions. Here is the combined summary of pages 910. This research presents a novel computational approach for predicting solid-liquid phase boundaries of molten salts using machine-learned potentials and thermodynamic integration. Focusing on sodium chloride, as a model system, the method demonstrates its potential for predicting phase diagrams in single-component systems. The study highlights the importance of long-range dispersion interactions in DFT exchange correlation functionals, with PBED3 showing the highest accuracy among the functionals considered. Molten salts play a crucial role in various industrial processes, including nuclear waste disposal and solar thermal energy storage. The authors employ neural network potentials, NNPs, in thermodynamic integration for predicting phase boundaries, emphasizing the significance of atomization energy of the crystal as a proxy for melting point prediction accuracy. In contrast, estimates based on lattice constants do not correlate as well. Different DFT functionals, namely PBE, PBESol, PBED2, and PBED3, are used to predict solid-liquid phase boundaries. The PBED3 functional yields the closest molar volumes and enthalpy differences compared to experimental values, correlating with its best accuracy for the phase boundary across the pressure-temperature space. By combining machine learning and thermodynamic integration, the approach efficiently predicts ab-initio level solid-liquid phase boundaries in molten salts, allowing for the prediction of phase diagrams in single-component systems using any underlying first principles method. The study's potential lies in its future applications for predicting phase diagrams of binary systems and solubility limits from first principles.